Okay. So, hello my dear, welcome to IMS GATE Academy. I hope you are doing well and your GATE preparation are going to be in right direction. I am Pragyabrat Tripathi. We continue with the lecture series of thermodynamics. So, what still I already finished here, we will discuss thoroughly about the some important concept related to the basic concept like a work transfer and work stored in the system. We generally see that work transfer is the thermodynamics process, that means P into dV, and store form of a work, one important work is a flow property, flow work. That means if you want to flow the process due to the pressure difference, there must be a work, and that work is stored. After that we will discuss about that thermodynamic concept of energy. So if you think about the energy, first we think about the what is the change and what is the transfer. There are two type of energy, two type of state of energy of a thermodynamics. I repeat, there are two type of state of a thermodynamics energy. First is the state of a point function, second is the state of a transfer. The point function state of a system is stored within the system. Sometimes it is called internal energy, we will discuss, okay? And other is the transfer, that means heat and work. That means that transfer is the boundary phenomena and it is a path function. And the state which is stored within the system, that is internal energy, we will discuss today. So there must be a two, according to a thermodynamics concept of energy, there are two states of energy. One is the stored energy, another is the transfer energy. The stored energy is the system property, transfer energy is the boundary phenomenon, okay? Like heat and work, we generally, the transfer through the boundary is the heat and work, and stored within the system, it is generally the total energy contained within the system. It may be increased, may be decreased, or remains constant. That means E2 minus E1, that means is energy at a point 1 and energy at a point 2, and the difference is the stored within the system, and that difference will increase or decrease or remains constant, okay? So stored energy, okay? Now, so thermodynamics, this study will complete that thermodynamic concept of energy. Now we will discuss, this is your thermodynamics concept of energy, okay? So thermodynamic concept of energy, there is two state of energy, one is the store, another is the transfer. Now today we will discuss about the first law of thermodynamics through that energy concept, okay? So we have in this context we have a two state of energy. One is the store, that means total energy content, delta E, one second, delta E, okay, delta E, okay, delta E. One is the stored energy within the system, delta E. That means this E is the total energy, mind it, this E is the total energy of the system, mind it. This is your total energy of the system, energy of the system, okay? This is the stored energy. That means if there is a system, this energy will have. And the change is responsible to the boundary. Who's responsible to change this total energy? The change is the boundary phenomena. That means other is change either dW and dQ. So these are not stored within the system. This is the boundary phenomena. So it is the transfer of energy. It is the change of energy. So this is a transfer of energy. Transfer of energy. So this transfer of energy will responsible to change this energy, okay? This transfer of energy will responsible to change energy. And there are two states. First state is store, that means this is a system property and this is the boundary phenomena, okay? Now today we will discuss about what is the relation in this two quantity of the energy, two state of energy. That will discuss according to the conservation of energy, and the conservation of energy will apply in the first law of thermodynamics. That means first law of thermodynamics, that gives the concept of energy, What is that? First law of thermodynamics, according to the first law of thermodynamics, we balance the energy. Very important. See beta, in thermodynamics, we have to balance three quantity. First, energy. Second is availability balance, and third is entropy balance. So in all the thermodynamics, we have to balance three quantity. One is the energy balance, other is the exergy balance, energy balance, exergy balance, and then entropy balance. We'll discuss very important, okay, that balance, and finally we'll take a table so that you have a clear about the how to balance the energy, how to balance the exergy, and how to balance the entropy. Okay, we'll continue with the lecture. Okay. So what is say that energy balance, the net change, see this is your change, see my dear, this is your change, net change, okay, this is your change. So net change, and that change we already told that either increase or decrease. That means the net change for which the system energy, the net change of the system energy, and that system energy is the total energy. That system energy is a total energy. That means that total energy either increase or decrease of the system in which during the process, and what is the process we don't know. There may be a reversible, maybe irreversible. Very important. Why? Because beta, this is the point function. That means state 1 to state 2 we can achieve either reversible or irreversible. Only will take state variables. So the change in state during the process, and what is the process we don't know, either reversible or irreversible, during the process is equal to, that change is equal to difference between the total energy entering, that means what the energy will enter to the system, minus the total energy leaving to the system. That's it. So what is the mean by that? The energy balance say that see, our requirement is the system, our perspective is the system. So we have to check the system energy either will change of the system energy either will increase or decrease. We have to do a energy transfer, मतलब हमें energy transfer करना होगा, and that difference of the energy transfer is decided by either the system energy will increase or decrease, and that will entry and that will exit, both are the boundary phenomena. Okay, so what we'll do, see beta, if this is our system, and system is any type of the system, mind it, either it is open system, either it is closed system, and the system will execute from point 1 to point 2 during the process, either in any process. Very clear. So this system, if we define the system, we fix the energy. That means we have energy. That means this is a state variable. That means if you define the system, either any type of system have energy. That energy is total energy content by the system. And what is the system? System is any type of the system, either open or closed. This is very clear. Now, if you want to check this change of energy, either will increase or decrease. So this change will possible. This change is possible. We take something entry, and that entry will take a positive. So generally we take heat in the form of heat, and exit, that means enter total energy entry in the form of heat will take, it is the example, it is not necessary that always heat, okay, and total energy exit W. That difference, that means what is in minus W, that will decide delta E. That means what is the system have energy will increase or decrease. See, this can never measure the absolute sense. We always measure the change, and this E is the total energy content by the system, and that delta E will responsible what is in and what is out. What the magnitude is in, what the magnitude is out. There must be a relativistic term. If in is higher than out, it must be increased. If in is less than out, it must be decreased. If there is no in the form of heat or work, that means if these two quantity are equal, that means heat is equal to W. When it is this quantity is equal, see my dear, this is very important. When these two quantity equal, when these two quantity are equal, these two quantity are equal during the cycle. the process executed during the cycle, that means total heat, that means summation of all the heat is equal to summation of all the work. During that, delta E is 0. That means delta E is 0 is the one possibility, is that it is an example. It is one possibility is that the system will execute in a cycle manner. So if there is any cycle, mind it, if there is any cyclic process, that means the system will execute from initial point to a final point, and that initial and final point are coincide to a single point, that is called cycle. During that, the property change is 0. That means if there is an engine working on a cycle, so what is the property change of that engine is 0. Property change either entropy or property change either internal energy, yeah, energy. Okay. Hi Sita. Hi, hello. So if we want to change, it must be, there is one example. It is not necessary that if there is a cycle there is thermodynamics during a cycle, it is always 0, but it is not necessary. It is only example. It is a reference point. Okay. Now, so what we will do, this is energy out. So we consider, this is in general, this is our general observation according to this statement. We take, this is our example. Okay. So in is anything, out is anything. During the difference of in or out, the system energy will increase or decrease. That's it. Okay. This is clear. Now, so we take this analysis with the help of little bit this concept. We have to go through that. See, so if this is our system, see my dear, if this is our system, okay, if this is our system, okay, if this system have energy E, this E is the total energy of the system, okay, this E is the total, mind it, very important, I'm telling you, E is the total energy of the system. Don't confuse with this one, okay? And if you want to check a change, so it must be of a process. So during that process, if you want to that there is something in, that means energy E, it is in, and this energy E, let's suppose out. So what say the first law of thermodynamics? That means what is say that conservation of energy? This system energy will change. That means is the total energy. So E is the total energy, and what is delta E? Delta E is the net total energy. Net total energy change. Not transfer. These are the meaning. Net energy change. Okay. Now, so what is the first law of thermodynamics says that the difference between in or out, in minus energy out, this will give the net energy change of the system. This is your system property and this is your boundary phenomena. Very important. This is your system property and this is your boundary phenomena. Okay. Now, this is very important. This change, this is not transfer. This is your change and this is your transfer. This is your transfer and this is your change. So, this change is equal to the net transfer. This is a transfer. This transfer is responsible for net energy. These are the basic terms. These are the like ABCD of a thermodynamics. If you don't know, you cannot able to solve any single problem of PYQ. Okay. So net energy transfer, very important. Net energy transfer. So this is your transfer. Net energy transfer in which mechanism? By by heat, very important, work and or mass. These are the responsible factor. These are the responsible factor. Heat, work and mass will responsible to net energy transfer. That means if there is a mass is in, also the mass transfer, mass is in, mass is out, there must be a boundary, cross the boundary, and due to that transfer of a mass, system energy may be changed. System energy may be changed. Okay. Now, what is this? This is what, beta? This is your system. Okay. That means this is your, we can write here, no problem. We can write here, no problem. So this is your change in internal kinetic potential energy and potential energy, right? So this change is either in the form of internal energy, kinetic energy or potential energy or all these one. That means this energy E contain the total energy content either in the form of internal energy, kinetic energy and potential energy, and other form of all energy like magnetic, electrical, but we can neglect as compared to this variables, as compared to this variable. So this is clear, okay, no problem at all. So this is called beta, very important. So this is called, this term is called conservation of energy for any system. This is called conservation of energy mind it, conservation of energy for any system during any process, for any system during any process, very important, during any process. This is very important, I'm telling you. Okay. Now if you introduce, and that is called energy balance. Energy balance. That is called energy balance. Okay. Now if this is the system and this is the boundary. Now if we write in little bit deeper manner, okay, sir, what is this one, how to write delta E? So we'll take this one. So there is one observation that how can write this equation? That means what is the delta E? Delta E is the energy change, net energy change of the system. This delta E is the net energy change of the system. This is your system. Okay, net energy change of the system, and that system will execute from point 1 to point 2. That means E final minus E initial. That means energy at point 2, that means total energy at point 2, state 2, that and total energy at state. So this is a state variable. Isliye we can write 1 and 2. It is not write I1, E1, E2, EI, E. So in the thermodynamics there are 3 notation, beta. We have to notation. There are 2 type of notation. What is that? I will give you one short here. What is that? See, this is important. Little bit you confuse. There is 1, 2, I and E. We are not denoting 4 point. So these 2 point are the denoted by the change of the system, and these are the something enter and something exit. So these 2 are boundary, depends upon a boundary, that means where the cross section, and these 2 are depend upon the inside the property. So if you define the property, we always write x1 x2. If you define the change, we always write xi or xe. So these are 2 terms. So this is your inlet and this is your exit, and these are the cross section. At the cross section, these are the at the cross section, not a point, but this is your point. These are the point, and this is your state. That means state 1, and this is state 2. Very clear. Okay. So we are denoting with the help of 4 terms. So always system, if you define the system energy, we take E2 minus E1. Okay. So what is that final equation? Energy in, that means I, if you write energy in minus energy exit is equal to E2 minus E1. This is very important. Very important. It is not a very important, but these are the very important observations there. Okay. This is very important. Okay. Energy in minus energy out is the change of energy of the system. Okay. And we have to write this is either in joule or kilojoule. It is energy. It is not a power, right? If you write a rate basis, so EI dot minus E exit dot, that means rate of energy in minus rate of energy out is equal to, we can write here, dE by dt of the system. It is right of the system. So it is it may be right in this form also. Okay. So this first equation, this is either in the form of watt or kilowatt. Okay, this is either in the form of watt or kilowatt. Okay, now, so this is the rate basis. When the system defined by the steady or unsteady, the system will define the steady or unsteady. We generally apply this equation. Okay, and only there is a energy balance. So this is precisely the first law of thermodynamics. Now, this is very important. So we'll take one very important things. What is that? See, my dear, example. Let's suppose take, what is that? Take number first. What is that? Let energy interaction by, let energy interaction by means of heat and work. Okay, heat and work. That means no mass transfer. That means we will only take the energy interaction only through the heat and work. No mass. If there is a no mass transfer, we are blocking the mass transfer. That means we are taking the energy balance of a closed system. Okay, closed system. That means only we are taking the energy interaction, either heat or work or both. That means no mass transfer. Mass transfer. That means precisely with the system will define now closed system. Closed system. right? Number second, very important, process is cycle. Process is cycle. We'll take process is cycle. That means this cyclic process may be reversible or irreversible, but the initial and final point are same. That means 1 equal to 2. It may be right. 1 point is equal to 2 point. Okay, property at point 1 is the same as the property of 2. What is the mean by 1 equal to 2? The property at point 1 is the same as the property at point 2. If we take these two example, if you take these two background of the first law of thermodynamics, so what is mean that? That means what we will do, if there is a cycle, if this is your system and system will execute in a cycle, this is first, okay, and in this cyclic process only heat and work are interaction. That means in this process heat input, that means Q, why input will take, why, because we take a positive sign, and work output positive, okay. So this is our cyclic process and only we will take heat and work interaction. So how to write? That means if this is a cyclic process, so in that condition change in internal energy, total energy is 0. Yes or not? Yes or not? That means if you apply that, that means what is in Q minus what is out W is equal to delta E, that is 0. Why? Because this is cyclic. Why will take a 0? Why? Because this is a cyclic process. Okay. So what is your equation? Q is equal to W. Now my dear, see the beauty. See the beauty. Now many students get confused here. What is that? Ki sir, I am asking like that, ki if we write for a system Q is equal to W, what is your observation? What is your background? So Q is equal to W, that means we are taking a closed system. That means there is no any mass transfer. Number first. Number second, the process is cycle. These are the very important, I am telling you. It is never written in the book, it's a crystal clear. Okay. So these two are very clear. That means beta, if this is our system, if this is our system, okay, if this is our system and now a system is defined, closed system, okay. If this is our system and let's suppose at this is your one boundary, this is your boundary, this system is surrounded by a different boundary and a different surrounding. Okay, so we take a small boundary through which a small heat will enter. That means dq will in, and a small boundary through which small amount of work will out, dw. Now, if you want the total heat in, that means in this will in, let's suppose this is in, this is in, this is out, this is out. So total heat is in is a cyclic integration. Why? Because this is a cycle. Cyclic integration of dq is equal to cyclic integration of dw. Cyclic, that means from this observation, what is the net heat transfer? Cyclic integration of dq is equal to cyclic integration of dw. This is very important. This is very important. Again, this is another notation. So in the thermodynamics, what is the meaning of that notation? You have to be very clear about that. Okay. So what is mean by cyclic integration of dq is equal to cyclic integration of dw? That means total energy in the form of heat will in is equal to total energy in the form of work is out. That means That means the system must be a closed system. Why? Because there is no any mass transfer. And the process must be a cycle. Process must be a cycle. Very important. Okay. Now, so our intuition is that we'll take what is the physical meaning. That means we have to find that dq is equal to dw. So what is the physical meaning? So what is the physically what does it means? Physically what does it means? That means, see, if we have, see, very important. That means if we have cyclic integration of dq is equal to cyclic integration of dw. What is mean? This is very important. What this says? This says that, sir, that if you transfer heat to the system, that means this is the positive. That means if you transfer heat to the system, system holds the capacity. That means system have a capacity. System have a capacity to do equivalent amount of work. That is Joule's experiment. Joule's say that work and heat are equivalent to each other. That means if we transfer heat to the system, system have a capacity to do equivalent amount of work. Equivalent amount of work. Very important. Equivalent amount of work. This is the meaning. That means if you transfer heat to the system, system holds the capacity to do equivalent amount of work. Okay, this is the physical meaning of this equation. This is the physical meaning of this equation. Okay, that means if any property, this is a thermodynamic plane. Let's suppose this is your y and this is your x. That means, and if the process is cyclic, if the process is cyclic, beta, if the process is cyclic, that means the area, this area represents heat also and work also, and they are equivalent to each other. That means, what does this mean? This means that Q net is equal to W net. Q net is equal to W net. This is also important. This is also important. Okay. So, if there is a cyclic process, in that cycle, the area is same as, why? Because in the cyclic process, heat transfer is equal to work transfer. This says that. That means we know that the curve under the area, if we project the volume axis, they gives the work transfer. If curve will project on the entropy axis, that entropy axis, they gives the heat transfer, reversible manner. So that heat, if will transfer, if the process is cyclic, the net work, that means if you supply during the cycle net heat, the net work will outcome. That is the meaning of this one. It is clear? It is clear, everyone? It is clear? It is clear? Okay. So, it is clear. Now, this is for the cyclic process. Now we take a non-cyclic process, that means process 1 to 2, but the property at point 1 is not at a property at point 2. Okay, that means, see this one. Okay, okay, see this one. Okay, beta. That means we have to, there is a system. If this is our system and the change of the system E energy will responsible to Q net and W net. Okay. Okay. And precisely if we transfer only heat and work, there may be a closed system. Okay. So this energy E, this system energy, that means system energy E, which is stored in the system, have a different forms. This E energy have a different forms, very important. What is that? First form is internal energy. Internal energy. Internal energy. Or you may say that intramolecular energy. Intramolecular energy. Internal energy, and this intramolecular energy or internal energy is associated with the temperature. That means this change of internal or intramolecular energy, this is associated with the temperature. That means associated with respect to temperature. Okay, with respect to temperature. That means, see beta, one thing, if there is no any temperature change of the system, that means if there is no any temperature, that means we have no considering any property with respect to temperature change, we cannot consider in this form of energy. Why? Because beta, when we discussing about the turbomachinery, that means fluid mechanics, in the fluid mechanics we cannot bother about the temperature change of the fluid. So in that case, this total energy, the component of in this total energy, that component is internal energy or intramolecular energy will neglect. That means during the analysis of a turbomachinery, this component of a total energy will neglect. Now the second one is the kinetic energy, potential energy, electrical energy, magnetic energy, this form of energy. Okay. See my dear, one thing is very clear, this internal energy, या intermolecular energy, या kinetic energy, potential energy, electrical energy, magnetic, these are all are microscopic energy. It is not macro, it is our microscopic energy. Okay, this is our microscopic energy. Now there is one thing is there. If we consider internal energy only in the form of intramolecular energy, that means associated with the intramolecular energy form of energy, that means this magnitude of energy, that means intramolecular internal energy magnitude of energy is higher as compared to kinetic, potential and electrical energy, then we can neglect this energy. Once we can neglect this energy, that during that system is called simple compressible substance. That means either you call a stationary system. Okay, very important. Note. What is the note here? Note is that if electrical, magnetic and surface tension effect neglected, in that situation, that is called simple compressible system. Simple compressible substance. So during the analysis of the first law or in the thermodynamics, we cannot bother about this energy. Okay, so one thing is very clear, the first law of thermodynamics which can be applied, that is only for the simple compressible substance. We can apply for that one, for the simplicity. Okay. Now, so this energy delta, this energy E have a composed of a numerous form, internal energy, this is the total energy, plus kinetic energy plus potential energy. Okay. Okay, and we cannot bother about the absolute sense, we can bother about the what is the change of the system. So delta E, delta U, delta KE and delta potential energy. Okay, now this equation generally it is in this form. So this is in this form, beta. Okay, so this total, and this is your total energy of the system. This is your total energy of the system. Energy of the system this is your internal energy of the system energy of the system, it is in the form of thermal energy. Okay, internal energy of the system, that means it is in the form of thermal energy. This is also called thermal energy. Thermal energy. That means why it is called thermal energy? Why? Because it is the responsible for the temperature change. Okay, now this is the change in kinetic and potential energy, you know that. Now if we neglect this change, that means, see my dear, if we neglect, that means if we take this change is neglect, change is zero. Mind it. That means what is the inlet, what is the initial velocity and what is the final velocity of the system in the system during the process is same, that is change is zero, and the change in potential energy is zero. If we take change in kinetic energy 0 and change in potential energy 0, that system is called a stationary system. That system is called a stationary. This line is very important. Okay, that means beta, if kinetic energy, that means if initial velocity v1 is equal to v2, that means kinetic energy change is 0, z1 is equal to z2, that means change in potential energy 0. Okay, 0. Okay, so in that condition, what is that? So in that condition, change in the total energy of the system is exactly is equal to change in internal energy of the system. Yes or not? If we write this one, that is called a stationary system. That is called a stationary system. That is called a stationary system. So our analysis is very concise at that condition. What is that? Now we analyze the thermodynamic first law of a thermodynamics, या conservation of energy for a simple compressible substance of a stationary system. Simple compressible substance of a stationary system. That means, what is that? Delta E is equal to delta U. What is your background? The background is that sir, the substance is a simple compressible and stationary system. These are the language of a thermodynamics. These are the language of a thermodynamics. So we can say that our what observation, our next point is that what we can, on what situation the first law of thermodynamics we can apply? Stationary system, stationary system of a it is visible of a simple compressible substance. These are the points. These are the points, and you have to able to understand each term. It is clear? Each term now you have to understand. Stationary system, that means it is neglect the effect of electrical, magnetic and surface tension. A stationary system, that means we cannot take a very much change at a microscopic level of the system, kinetic energy and potential energy. Okay? Okay, beta? It is clear? Now, we have to go within little bit deep. What is this internal energy? What is this internal energy? See, my dear. See, look at this figure. Once look, this is the observation. See, if you have a glass of water, right? If we have a water content in this one, okay? What is we observe that this water have itself a temperature, agitation temperature. That means it's have a temperature. Any system have a temperature. So that system have a temperature. That means, does the glass water sitting on the table have any energy? You think like that. That means, if there is a glass of water and it is rest on the table, in the water, there may any energy? Yes. No apparent energy of the glass of the water on the microscopic scale. Microscopic level, on the macroscopic level, this content of the water inside the glass have a no energy, number first. That means it's have a energy or it's have a not energy with respect to your approach. If you take a macroscopic approach, there is no energy. But if you take a microscopic level, the molecules due to a temperature have a random motion, yes or not? All have a random motion. The molecules have a random motion, yes or not? The molecules have a random motion. That means it have a kinetic energy is the part of my dear, it is internal energy is the total energy at a microscopic level. Internal energy is the total energy at a microscopic level. In that microscopic level, the molecules will be a motion, random motion. The molecules have a random motion. Why? Because it's have a threshold temperature. That part of the motion of the microscopic level of the molecule, that is kinetic energy. That means what we write, delta Ke this one at a microscopic level. That means the internal energy, one part is due to the motion of that microscopic molecules. Second, the molecules itself have a vibration. The molecule itself have a vibrating. That means it will vibrate. It will vibrate. That means the bond. Why? Because the molecules have joined its by bond, and that bond will due to that bonds, that means the force of attraction will there. Due to that, there must be a vibration. That means the vibration can be measured on the potential energy. That means molecules attractive force, that means cohesion, are associated with the potential energy. That means if there is a bond, it must be a bond. That bond is responsible to vibrate the molecule. That will measure the change in potential energy. And these two are at a microscopic level. Why? Because the fluid as a whole at rest. So the molecule, if you take any point in the glass and track them, so in a point there have a numerous number of molecules, and that molecules have a two status. First status is a motion, random motion, microscopic. You cannot observe. It is a microscopic level. So it will measure the kinetic energy. And molecules have itself a bond. At that bond will due to that bond, the molecules will attract by the cohesive force. That will measure the potential energy. So at a microscopic level, a glass of water have a two status. One is the kinetic energy, other is the potential energy. And it's have a temperature, so it's have a internal energy. Okay, so the energy content within the system, delta E, energy content by the system, that means change in energy, is due to the internal energy that is associated with the temperature, and that is associated with the microscopic level. Okay, this we have. And if we neglect this two effect generally, so that analysis going into consideration of stationary system. Okay, if we neglect this one, why? What is the basic concept behind the negligency? That means these two sum of energy component is much less than this energy. So we can neglect. Why the much energy? That means the motion of the all molecules motion, that means V1 initial and V1 final are same. Potential energy, there is no much more of the datum, so potential energy change will neglect. So all over the neglects in same. So this total energy change of the system is exactly equal to the change in intramolecular energy. That is called a stationary system. A stationary system. So what is the mean by the stationary system? Now you have to clear. Okay, that is our stationary. Now see this one. What is the internal energy? See, there is a molecules, that means there is a atoms. Yes or not? This is your atoms. This is your atoms. One atom, different atoms, different atoms, and that atoms is connected by the bonds. That atoms are connected by a bonds, different bonds. Now, due to its thermal energy, internal energy, also called a thermal energy, very important, okay, is the energy of an object or substance, that means glass of water, is due to the kinetic energy, and kinetic energy is due to the motion, random motion of that molecules measured by the kinetic energy, and the potential energy associated with the random motion of all the particles that make it. Okay. So internal energy is defined as the energy associated with the random disordered motion of the molecules. That means internal energy we can measure is measured due to the association with the disorderness of the motion and random motion. That means there must be a bonds due to vibration, that means measure the potential energy, and there must be atoms will be random motion. That two combines measure the internal energy. Okay. So now if you understand the energy component associated with that, means a state of energy. Now during the first law of thermodynamics, if you study the state of energy beta, a state of energy, so that state of energy will already covered. Why? Because the state of energy we can measure the total form of energy, and that total form of energy is a microscopic level. Microscopic, not macroscopic level. And microscopic level measure have a two status. One is the due to the atoms random motion, and other is the bond vibration. There is a vibration of the bond. So the random motion of the molecule measured by the kinetic energy change, and vibration of the molecules measured by the potential energy change, and that all combined associated with the internal energy. Okay. Now initially in the first attempt of the class, we already discussed that what is the first law for a cycle. That means the total net energy heat transfer is equal to net work transfer. Now we will consider the energy transfer. That means first law will apply for any process. That means if we have a plane, thermodynamics plane 1, y and x, and there must be a state point 1 and there must be a state point 2. So if the state point 1 is fixed, 2 is fixed, so E1 is fixed, energy at 1 and energy at 2 is fixed. And now we join the process, different process. It is visible? 1 second. Different process. Different process. Okay. So there is a different process. This process, let's suppose this process, this process. Now we define the process during the first law of thermodynamics for any process. That means what is meant by any process? Any process, that means either reversible or irreversible. Okay. Any process, reversible or irreversible process. Now see my dear, so if you draw any thermodynamics process, let's suppose this is your thermodynamics plane. Let's suppose this is your y property and this is your x property. Okay. Now we take 2.1 and this is your point 2 is two state of the system, and we join for a different process. Let's suppose 1 to 2 join via path A, 2 to 1 join via path B, and 2 to 1, let's suppose another path joined via path C. Okay. So my dear, if you look very carefully, sir, 1 A, 2 B, 1, this is one cycle. 1 A, 2 C, 1, these are two cycles. And those two cycles are connected by the three different process. Process A, process B, and process C. So there are two cycles, and we have to define already what is the first law of thermodynamics for a cycle. Okay. So process A plus B. Okay. Process A plus B. So process A plus B makes a cycle. Okay, process A plus B. This is one cycle. And what is the name of the cycle? This process A and process B is a cycle. So this is your cycle. And what is the cycle? 1 A 2 B 1. This is one cycle. 1 A 2 B 1. This is one cycle. Okay. So we apply integration, cyclic integration of dq for this cyclic process is integration of dw. Yes or not? Okay. So if you integrate, this is for cyclic, total cyclic. So if you integrate 1 to 2 dq via path A, yes or not, plus 2 to 1 dq via path B, yes or not, is equal to, this is total, process 1 to 2 dw via path A plus 2 to 1 dw via path B. C, sorry, this is your C via path C. It is clear? So this is the method how to apply this cyclic to the process. So in this cyclic, there is a net heat is equal to net work. So what is the net heat? Heat transfer during the process A plus heat transfer during the process B. What is the net work transfer? Work transfer during the process A and work transfer during the process B. C. And the process is 1 to 2, 2 to 1. Okay. So this is for the process A to B. Now process A plus C. A plus C. This is also cycle, yes or not? This is also cycle. And this, what is this cycle? 1 plus A plus 2 plus C and 1. This is another cycle. So for this cycle, we also apply cyclic integration of dq is equal to cyclic integration of dw. Why? Because this is cycle. So for that cycle, cyclic integration 1 to 2 dq via path A plus 2 to 1 dq via path C is equal to cyclic integration 1 to 2 dw via path A via path C. Okay. Now, if you subtract these two equations, that means this is equation number first, this is equation number first, and this is equation number second. Okay. Now, if we subtract these two equations, if we subtract this equation, that means if we done like that, now what is your outcome? Second minus first. If you do the second minus first, this is directly come 2 to 1 dq minus dw, look at this one, via path B is equal to 2 to 1 dq minus dw via path C. Very important. This is very important, I'm telling you. If you subtract this to 1, if you subtract this to 1, this one cancel, only this one, this minus this minus this, and this one cancel, this minus this. So if we are rearranging that, so if you are rearranging that, so what we observe, the observation is that, sir, This is very important observation. Ki sir, that means, see very important, I'm telling you. This is your heat transfer minus work transfer via path B of a process 2 to 1. This is your heat transfer minus work transfer via path C of a same process. That means if we take any process 1 to 2, if you take any process 1 to 2, this is your y and this is your x. If you take any process 1 to 2, this is 1, let's suppose, and this is a 2. If you take any process 1 to 2, if you take any process 1 to 2, that in that process, and if you take any another process, this is process A, let's suppose this is process B, and C, and this B and C process are same sense. B and C process, that means heat and work transfer between this process and heat and work transfer between this process via point 1 to 2 to 1 are same. That means 1 to 2 via path B and 1 to 2 via path C. This is not a cycle, this is a process. That means 1 to 2, yeah, if you change the integration, this will also change. So 1 to 2 via path B is equal to 1 to 2 via path C of the quantity are fixed. That means this quantity and this quantity, the difference of work, heat and work is fixed for any process, for any path, That means this quantity, which quantity? dq minus dw of the state 1 to 2 are path independent. Are path independent, it is not depends upon the path. That means either path B or either path C, the quantity dq minus dw is fixed. That means for this path dq minus dw and for this path dq minus dw is fixed. That means the quantity dq minus dw, that means this quantity dq minus dw is path independent. Path independent. If it is a path independent and it's only depend upon the state point, that means it is a point function. And if it is a point function, it must be a property. See the beauty. dq is the path function, dw is the path function. So if you subtract two path function, it gives the point function. It gives the point function. Why? Because if you differentiate these two one, it will independent of the path. This is the beauty. This is the beauty. That means it is fixed for any path. That means the quantity dq minus dw, it is a point function. Point function. That means state variable. That means state variable. That means property of the system. Properties of the system. It is clear? It is a property of the system. That means this quantity is a state variable. This quantity is a state variable. Integration. Obviously, it is an integration. That means integration. Okay. Okay. Now, and that point function या property of the system is called, what is called? This is called internal energy या total energy of the system. Total energy of the system. And if the system is simple compressible and stationary, that means this total energy of the system is equal to the internal energy of the system. That means we can write here dq minus dw is equal to dE. This is very important. How to write this equation? This is very important. Why? Because this is the path function, this is the path function. Difference between two path function is the point function. So difference between two point function, path function energy, difference between two path function is equal to the difference between point function. Point function. Difference between the point function. Okay. And you know that what is E? What is this E? This is the energy of a closed system. Yes or not? Closed system. Why we call closed system? Why? Because only heat and work are interaction, no mass transfer. That in that sense is a closed system, but it is not a energy of a closed system. It is for open system. But with respect to this quantity dq and dw, we disregard the mass transfer. With respect to that perspective, this is called energy of a closed system. But this is not necessary that it is the energy of a closed system. It may be energy of open system. Once we can take a mass transfer also. System. Okay. And it is a property and is a property. Okay. This is clear. Now, that means amount of energy stored in a system, and it is a property stored in a system. That means point function. Okay, that means point function. That means point function. It is clear? It is clear, beta? This is clear? So, at that time, we have a three different form of first law of thermodynamics. What is that? Very important. See, my dear, we can write like that: dq is equal to du plus dw. We can write also q is equal to delta U plus W. We can write like that. Q1 to 2 is equal to U2 minus U1 plus. These are very important, I am telling you. This are the language of a thermodynamics, okay? How to write. So, these are the three form of equation, okay? These are the three form of equation. Now, if you tell about that, this equation, what says that these are the same equation, but the physics are different. What is the physics of this equation? The physics of this equation is that, sir, this equation will be when there is a small amount of transfer. When there is a, this is for, and this is all for the cycle, is process, not for the cycle. This is for the process. If this is for the cycle, this term, this term is neglected. And this is the process 1 to 2, and this is your net. This is your net. This is your infinitely small, and this is your transfer for the process 1 to 2. So if the process is given, you can write 1 to 2 process is given, you can write Q12. If there is no any process, net it is given, so Q is equal to delta U plus W. If there is a very small quantity is given, dQ is equal to du plus dW. And cut mark denotes the path function. Okay. So what is the validity? Validity. What is the validity, beta? This valid for, what is the valid? Very important, I am telling you. How, when it is valid? See, these are the valid for, this is what, beta? First law of thermodynamics, first law of thermodynamics for any process, yes or not? For any process. This is very clear. For any process. This is the first law for any process. Number second. What is the number second? Closed, then bracket stationary. Close and stationary. One second. Stationary, close and stationary system at equilibrium. Yes, sir. So these are the very important things, how to apply this equation and how to write. So this is your first law. Okay. For a process. Now, in the next session, we have to see what is the outcome of this equation, how to apply, with the one example is there, okay? How to apply this equation through examples. That means what is the practical implications. If there any power rating of the any system it is given, that power rating, that in that observation, it is valid or not, this equation. That means what is the physics, how to apply this equation for a particular engineering system. That means if there is any device you have to given, accordingly that device, the power rating or anything is provided to you, and you have to check that information given by the operator, it is true or not with the help of this equation. This is very powerful equation. It is not remembering, always you can remember. No, what is the implication? You can check whether the information given by the any system is true or not. That means what they claimed by the operator, that claim is true or not, you can check with the help of this equation. This is the very important equation. So in the next session, we have to use this equation in the practical situations. Whether you feel in the regular life, you can feel it, and if you know really how to use this equation, that gives the one motivation to you as an engineer, that you can judge anything for the particular system. Yes, the information provided by the operator is correct or not. Okay. So up to that, I ended here, and we will continue with the next session. Okay. And from here we continue with the next session. After that, there must be some observation is there, checkpoint is there, so that you can better feel of this equation. Okay. Thank you. Bye bye.